Hello everyone, this is Linesh Dave, and in the next few minutes, I would like to take you through a very simple solution for the Kaggle computation, evaluate the cars. And you had already received instructions a few weeks back to join this computation, and also a video was posted to provide more details and information. Hope you found them useful. Now, in case you haven't worked on this Kaggle computation yet, because you don't know how to start or form a solution and post a submission file, then you'll be able to get a very good idea to do just that without much fuss and complexity. Now, you may not want to copy this code that I'm going to go through or use extracts of it to form your solutions, as that would be considered plagiarism and your submission will be rejected. It will also violate UMGC's code of conduct for assignments and submissions. I would rather suggest that you pay attention to this video, get a good idea of how simply a code for this computation can be written, and also post the created prediction file on the Kaggle website. So with that, let me dive right into the code. It is the R code, and a few basic R packages have been used to develop this code. It is by no means a foolproof or the best code written or available, best code written or available for the problem in hand, but a code that just gets the work done in a simple manner. Okay, so as you can see on the screen now, this code is divided into 10 different sections, and they are the header information, clean up our environment, describe and load packages, define local variables, read CSV files, define training controls, train different models, analyze created models, predict target using the best model, and then finally build the submission file. Now the header information is just consisting of some information about this computation, about the class and the author, so just some header information here captured. The real execution actually starts here in the cleanup R environment, where the task is to clear all variables and the plots in the environment. Okay, so let's run this, and that's what we're going to generally do here. We're going to run I'm going to explain the statements of the section, then run the statements in real time, show it to you, and then there are going to be like one or two statements that take a long time, where I'll have to pause the video and then come back again when the statement execution is over. Okay, the next section is about loading the packages, where, and as I mentioned earlier, we're making use of few packages, such as caret, E1071 for miscellaneous functions. There's C50 for C5.0 decision trees. There's pragma for practical, numerical, mathematical functions. So this for statement here is basically, taking in all these packages, checking if they are installed. If not, it will install them. And if they're installed already, then they would go through loading them in the environment. So let me run this. We'll just be finished in a few seconds here. So right there, we are done. Next, we go on to define local variables. In this case, we just need one variable, just a files path. It's a path to file, or the files, the dataset files, the CSV files that are stored in my local PC here. Okay. All right. So let's run that. And then the next section, we're going to read the CSV files and assign them to objects, just the DataFrame objects. We are also going to do one more task here. We're going to, once the data frame is created or the CSV file is read, for the train and the test data set, we are going to drop the car.id column because we're really not going to make use of them while training or testing. Okay, so let's go read the training set, remove the car ID column, and then we're going to read the test data set. Same thing, we'll remove the the car.id column. And finally, we'll read the prediction file, the file that we need to do the predictions on. And it's called the car's final prediction. Now, in this case, we haven't really dropped the car.id column because we really need to use that. And for our predictions and also for the submission, one of the columns is the car.id column. The next is defining some training controls. First and foremost, we'll set the seed so that we can get we can reproduce this results every time we run this code. And then we are going to set some training parameters. We're going to use the method as repeated cross validation. The number of folds we're going to use is 5. We're going to see the repeats are going to be the whole process is going to be repeated 5 times. We're going to save all holdout predictions. We're going to also compute the class probabilities, and we are also going to print the training log. Okay, so the basic training parameters that we'll be using during creating the models, training the models. Okay. Next, we are going to create a data frame for all combinations of factor variables to plot predicted responses. So basically, every once we run or when we train the model with different parameters, we want to store the results, right, in a data frame against the parameters that we've chosen. So we are going to create a grid for that, or a data frame to hold the predictions or the results for those parameters. Okay, so for the first one is the C50 grid. We are creating the grid here for the C5.0 tree model. So as you can see here, once you execute this command, this particular data frame is created with 10 observations of 3 variables. So the 10 observations is because of this array that's being used as value to trials column. So it's going to set 10 observations, and the model is going to be tree, and the win now is set to false. Okay. Next, we'll build a grid parameter for the neural network. Okay. Oh, this got run twice, but not a problem. We'll run the neural net grid, and in this case, for every decay size ranging from 0 to 0.0001, 0001, 001, and 0.1, you're creating 10 observations for each of these decay size. So there should be 50, and as you can see here at this bottom here in the global environment area, this grid is created with 50 observations of 2 variables, size and decay. Okay. Now we're ready to train different models. So for this particular code, we're going to create 3 different models, and then we're going to analyze the models and choose the best one. And there's no set way here. This is, once again, by no means the perfect code, by no means the perfect models being used. You can train as many models as you want, analyze all of them. You can train the models with multiple parameters, more than what have been chosen here. So sky's the limit, right? We're just showing you the simplest way to write a code and get the work done, right? So we'll start with training a CART 5.0 model, decision tree model. And as you can see here, we're using the train data set. We're using the C5.0 method. We're using the grid so that the results could be stored there against the parameters. And we're using some of the training parameters that we've already set. in this fit control. So first we'll train this model, and this is going to take few seconds. Shouldn't take a long time, so we can do this real time. And once that's completed, we'll train the other model. So the next model that we are going to create is the random forest model. And the same training data set, the method, and we're going to use some of the basic training parameters that we set earlier. In this case, we are not using a grid to store the parameters. So we are not going to be changing a lot of parameters here for the random forest. We just set it once. Okay, this may take a little more time than the decision tree, just understood, but still it won't take a long time to pause this video. We can just hold on here, let it finish, and once done, we'll get to training the next model. Now that will take some time. It's a neural network model, and as you saw that we already going to train it. We have the basic parameters. We have the grid, which is 50 observations. So 50 different ways or 15 different combinations of parameters being used to create this neural network model. So definitely it's going to take some time. So I'll be pausing the video in between. Okay, so it has started creating the neural network model, and let it go and finish. Pause the video here, and I'll come back once done. Okay, you're back. I know for you it may be just a short time, but actually the video was paused, and this took actually a few minutes to compute and complete training this model. Okay, so now that we have created or trained all the three different models, the next will be analyzing these models. Um, First, we'll put all these different models in results in a model and in a results object. And once that's done, we can then, once they're sampled, they are they resampled, we'll kind of just look at the summary of the results, and it will kind of show you all the numbers again, for the accuracy and kappa for all these three different models. What was the mean and median and so on. The best way to really look at this data is via a couple of plotting techniques. One is the BW plot and the other is the dot plot. So let me run the BW plot. And as you can see here, although all these three different models, from accuracy perspective, they appear to be close, but neural network definitely has an edge over both the other two model types, the C5.0 and random forest. And surprisingly, C5.0 also did slightly better than the random forest, as that's what it looks like for me, that it is slightly better. And if you look at even kappa, the kappa values also suggest that neural network is better. The next is C5.0, and then the last is random forest. So surprisingly, random forest did not do as well as you may have expected. Now, so again, this could be seen through another plotting technique, or the plot that you could make use or you could use is this dot plot. It will show the same results. It's just that in a slightly in a different form here. Okay. So now that we know neural network is the best model here, we can now do the prediction for the test data set and check for its accuracy. So we'll just use the predict method. We'll use the neural network model, and the data that was used is the car test data frame, which is the test data set. And then look at the table here, and as you can see, the table gives you an idea about what was predicted against the actual values. So as you can see here, the value ACC, or the class ACC was predicted, or the acceptable class was predicted for 69 acceptable cars in the data set, one good car in the data set, and three unacceptable cars. So overall, it did a good job, but still, it was not 100%. But maximum acceptable cars were predicted correctly. Same for the good class, right? The good class was predicted for 12 good cars and two very good cars. The class unacceptable was predicted for 224 unacceptable cars and one acceptable car. But still, overall, a very good performance. Pretty close. So let's find out. You could have also some of the other stats, and by going through the confusion matrix here, and it will give you some other numbers as well. If you just look on the top here, it will give you the accuracy, which is almost 97.22%, which is pretty good accuracy, right? And once again, you can play with the different parameters. You can look at other models, and probably you may even get better than 97.22. You could get 98, 99, and who knows, even 100%. Okay, so play around with the different model types. Okay, and here in this case, let's finish it with, it just gives you a summary statement, a summary of all predictions. It predicted 73 as acceptable cars, 14 good cars, 225 unacceptable cars, and 12 very good cars. Okay, now having some confidence in this particular model that we got by predicting against the test data set, we'll now do the prediction for the unclassified data that was given to us for prediction. So we'll run that, and it just completed this prediction here. Now let's look at the summary here. So the summary is that we got 97 acceptable cars, 15 good cars, 302 unacceptable cars, and 20 very good cars, right? And we don't know its accuracy, right? Because that's, this was an unlabeled data. So next, what we can do here in order to even find the accuracy or how we did with our, with the unclassified data, we'll have to build the submission file. So we can build the submission file with two columns. So here we're creating a data frame with the car.id column and the prediction class that we just predicted, right, on the unclassified data. We are just going to then name the columns as car.id, and the next other column is class. And then finally, using some name, just give a name to the CSV file, we can just write all this entire car output data frame to a CSV file. And so we'll just output to a CSV file, and then we are done, right? So from a coding perspective, we are done. The next thing that we do here is we come to this competition page on Kaggle. And of course, assuming that you would have logged in. And once you've logged in, you go and hit submit predictions. And in this case, if you have not accepted the rules yet, it'll ask you to accept the rules and bring you back to this page. And now on this page, you'll see that you'll be able to upload the submission file by clicking this icon. And once you pick the file from your local PC, you can just then click on make submission, and it will do the submission for you and give you the results based on the 70% of the data. The other 30% of the data is going to be tested when the competition is over. But you'll get a very good idea of how you've done, whether you want to improve the code or not. Maybe you want to try with other models, try other parameters of the models, get to a point where you get better and better accuracy on on training the model, and also on while testing the testing the model with the test data set that was given to you. Okay, so Try all that, and if any questions on this video or the computation in general, please post it against the thread in the class discussion area. Okay, so good luck again, and we'll look forward to your submissions. Okay, thank you.